Hi everyone. So today we're going to continue on 10.3 linear equation. So before we get to the last two examples that I want to talk to you about, um, maybe I mention the following things first. So two things that are important that I didn't get to mention about this method is the following. So two things about this method are important. And so what are these two things? So number one, uh, you must put the differential equation into what we call normalized or normal form, or normalized form of y prime plus g of y, g of xy equal to f of x. The reason why, because if you don't put it into this form, you may identify the function y incorrect, the function g of x incorrectly. So you must put this differential normal form before you can identify the function g of x. Because if that is incorrect, that would mess up your exponential multiplier m and therefore mess up the rest of the problem. And one of the most common mistakes to be made is that they mess up the sign of g of x and therefore mess up the rest of the problem, and you might think it's a minor mistake, but it is major when it affects the rest of your entire questions. All right? So the second thing that some of you actually might be thinking about is the following. Is this the equation y prime plus g of x y equal to f of x, and the equation m of x y prime plus I guess g of x m of x y equal to m of x f of x. These two equations are equivalents. The reason why they're equivalent, because m of x is an exponential function. And so it is never zero. That is the issue. See, the problem is that when you multiply an equation by something, it doesn't necessarily create an equivalent equation, because of the fact that what you're multiplying, if it equal to zero, it will make the entire equation equal to zero, become zero equal to zero. But it doesn't mean that the product have to be the same. Meaning, in this case, think about it. It's entirely possible for 0 times A to be equal to 0 times B, because they both equal to 0, where A does not equal to B, which is entirely possible. Because the fact that you multiply by 0 cannot trivialize the entire equation and just make it equal to 0 equal to 0. So the problem is that this would not happen in our case, because our m of x is an exponential function, so it can never equal to 0. So we can safely multiply and divide our equation by m of x, which is perfectly okay because it never equals 0, so therefore I would not be divided by 0. So those two things are very important there for you to think about and make sure you understand, because you want to make sure that your math is not going to get invalidated because of some unexpected things that you might have done. So with that being said, I'm going to go ahead and do my last maybe 2 examples. I'm going to try to see if I can do 2 examples. But I also don't want this video to be too long. So let's see what happens. So here's my first example. So my first example is pretty straightforward, pretty simple. Okay. So what we're going to do is the following. So is we're going to do a mixture problem. So let's see if we can do a I'm going to try not to write out the entire problem, but how about just maybe draw your diagram to kind of show you how it looks like. So let's say we have a tank, just like the last problem that we have done with the tank. Okay, and let's just say this is another 100-gallon tank. And yes, I do like to use 100 gallons because 100 is a nice number to work with. And let's say with some kind of salt, some kind of solution going in at 3 gallons per minute. And then the liquid also exit out 3 gallons per minute. So that way you can maintain the volume of the tank inside. And let's say that we start with 10 pounds of salt. So let's say a full 100-gallon tank contain 10 pounds of salt dissolved in water. Okay, now let's say there's a 3 gallons a solution of is being run into the tank. At let's say 3 gallons per minute. And of course, and the excess solution is drained out of the tank at, of course, 3 gallons per minute. So that way we don't have a change in the volume. And of course here we assume that as soon as the liquid enters the tank is fully mixed so that the concentration almost immediately become the new concentration. Okay, of course that's a little unrealistic, but if we want to actually create a more realistic scenario where the liquid go in and then gradually mix with the rest of the tank, it will really complicate the differential equation a lot, because then you have to talk about some kind of gradient measure of how the solution is mixed, how in the top of the tank the solution might be different concentration than the bottom because of the mixture, but that would just be way too complicated for us. So we want a simple system to start with. Now, let's assume the following. So one thing that you probably noticed I didn't give out is the concentration of the liquid. So let's say the solution being run into the tank has a concentration. So unlike the last problem that we did back in 10.2, where we have a fixed concentration, because if it's not fixed, you won't be able to solve the problem. So here, how about the solution has a concentration that's varied? So let's say the solution being run into the tank has a concentration that increases slowly according to some function. Let's say this function, c of t is equal to 1 minus e to the negative t over 100. So that formed the concentration of the liquid that's going in. So now what we're going to try to do is, let's see if we can find s of t, that modeled, the amount of salt in the tank. All right. So let's see if we can figure this out. So, just like the last time we do a problem similar to this, what we need to do is first come up with a differential equation. So remember, the differential equation basically talk about how much salt is going, how quickly salt is going in versus how quickly salt is going out, and that is defined by the derivative ds over dt. And that's equal to the amount of salt going in. So the amount of salt that's going into a tank would be based on the concentration at T multiplied by the rate of the liquid of the solution going in, which is 3. So here, if you think about it, this concentration must be a unit of a pound per gallon, while this rate is gallon per minute. So when I combine these two together, it becomes pound per minute, and that become a mass or amount of salt over time variable derivative. So that's the rate in. So now how about the rates going out? So the rate going out is exactly the same as 3, but that's gallon per minute. I do need a concentration, and the concentration would simply just be equal to S over 100. Because that would be S amount of salt within 100 gallons of liquid. So that become our differential equation. So now it's just a matter of solving that differential equation. So let's see if we can do that. So I'm going to, let's start over somewhere over here. So ds over dt would equal to 3 times 1 minus e to negative t over 100 minus, I guess, 3s over 100. Or actually, better yet, I'm going to write it as this. I'm going to write 3 over 100s. So now what I need to do is put it into what we call the normalized form or normal form. So how do I do that? Well, remember, I will put all the unknown function and its derivative together on one side of the equation and everything else on the other side. So if you think about this equation right here, so if you're getting a little confused, I'm going to help you out. So in this equation right here, our s is basically the y. Our t is basically the x. That's basically how it works. So therefore, I'm going to write it as this way. I'm going to write as s prime, which is ds over dt, plus 3 over 100s equal to 3 times 1 minus e to negative t over 100. So now I have it in what we call normalized form. So this is my g. This is my f. Now, once again, the G really, the F really doesn't matter, okay? So now what I'm going to do is I'm going to go ahead and try to solve this differential equation. So let's see how that works. Okay, so I have my G, so I'm going to go and find my I'm going to go and find my exponential multiplier. So I m of t in this case, not x, because our independent variable is t, is equal to e to the integral of 3 over 100 dt. Yes, it's dt, not dx, because here our independent variable is t again. So that just comes out to be e to the 3 over 100 t. So now my equation would be e 3 over 100 t s prime plus 3 over 100 e 3 over 100 t s equal to, I guess I will multiply that to this thing over here too. So I'm going to go and write out what I'm going to multiply, and then I'm going to actually try to multiply it and see what happens. Okay. Now, obviously, I don't want to keep this side the way it is, because that will require me to do some kind of integration by parts or something, because I have a product between two things. So I'm going to go and take this thing and multiply into my parentheses and see what I got. So that would be 3 e to 3 over 100t minus 3 e to the 2 over 100t. So that's nice. And remember, on this side, this is nothing more than just e 3 over 100t s prime. And that should equal to this side, which is 3 e to 3 over 100t minus 3 e 2 over 100t. And so now what I need to do is integrate. So if I integrate, the left side would just take away the prime. The right side I have to integrate these two things. So what happens when I integrate this right here? When I integrate this right here, it becomes 100 over 3 times 3, which is 100, e to 3 over 100t, minus, it will be 3 times 100 over 2. So therefore become 150 e 2 over 100t. And of course, don't forget the plus c. And so now what I'm going to do is I'm going to multiply the entire equation by e to the negative 3 over 100t. So that would balance out the e3 to 3 over 100t. And that will give me this equation right here. S of t is equal to 100 minus 150 e to the negative 1 over 100t plus some constant c e to the negative 3 over 100t. Now, since we know our initial condition S of 0 equal to 10, because we're told there were 10 pounds of this salt inside the solution to begin with, I can now say 10 is equal to 100 minus 150, and e to negative 100t become 1, plus c times e to the 0, which is also 1, so become plus c, and therefore tell me that c must equal to 60. So this is my general solution. Now we just find our c value. Now I can present my solution. In this case, our solution S of t would equal to 100 minus 150 e to negative 1 over 100t plus 60 e to the negative 3 over 100t. That equation will now model the amount of salt in this problem. Now, something interesting that I do want to point out is the following. If you look at this example right here, notice that if this process go on forever, both of the e to the negative 100t and e to the negative 300t will become 0 eventually. And therefore will tell me that if this process go on forever, this would just equal to 100. Okay? Now, if you think about it, it also makes sense because eventually the solution inside will be overcome by the concentration of the solution that's going into the tank. And this solution right here generates a concentration of 1. And so for a 100-gallon tank, it should have 100 pounds of salt in it. So some of these things are interesting to think about. Now, the next example is absolutely extremely very important because the next example is Newton's law of cooling, which basically talk about how our coffee in the morning is cooled down. And that's extremely important because then we want to keep our coffee hot when we drink it. So here's the example, Newton's law of cooling. So now, obviously, Newton is not the only person who realized that when you leave something in a room, it would eventually cool down. So that's not his accomplishment. His accomplishment is that he actually figured out how the relationship is. Okay? So here's what Newton's law of cooling states. Newton's law of cooling states that the rate of change of the surface temperature let's say U of t of an object, the rate of change is proportioned to the difference the difference between u of t and f of t, which is the surrounding temperature. So that's what Newton discovered. Not that he discovered that he released something out in outside long enough, it will cool down, but rather he figured out that how quickly the object's cooling down is actually determined by the difference between the object and the surrounding temperature, which once again, if you think about it, that seems very obvious and very typical, very like right to our expectation. But he was the first person to kind of come up with a mathematical formula that would actually describe that. And of course, the reason is because the relationship is actually described by a differential equation. So this equation, this relationship, can be represented as a differential equation. Shockingly, because this talk about the rate of change, which is derivative, so can be represented by a differential equation. Maybe I should say there can be represented as the differential equation right here, du over dt equal to some constant, and then the difference between f of t minus u of t. And of course, in this scenario right here, u of t is the unknown functions that we're looking for. Okay, so now what we'll go do is we'll go try to attempt to solve this differential equation using exponential multiplier method. So how are we going to go about doing that? So first I'm going to do is I'm going to write in normalized form. So y u prime is equal to k times f of t minus k times u of t. Or you know what, actually maybe better yet, I'm just going to write as k times f minus k times u. Okay, yeah, because we just assume that we know the t is the independent variable. So now that's not in normalized form, so I'm going to go and put that in normalized form. That would be this. And now I can go ahead and find my exponential multiplier method. So my m of t would equal to e to the integral of k dt, and therefore equal to e to the kt. Good. And so now what I'm going to do is multiply the entire equation by e to kt. So e to kt u prime plus k e to kt u equal to k e to the kt f. And so now this would form e to the kt u, the product prime, and so now I can integrate this to figure out the solution. So e to ktu would equal to the integral of this thing. So k is a constant. I'm going to pull out the k. Actually, you know what? I'm going to leave it inside. Integral of k e to kt f of t dt plus some constant c that we don't know. And now solve for u. Tell me that u equal to, I'm going to pull out the k, e to the negative kt, integral of e to the kt f of t dt plus c e to the negative kt. And that become what we call the Newton law of cooling formula. Now, but of course, that does not look like the Newton law of cooling formula that you know. Well, of course, because the Newton law of cooling formula that we know, that you have learned before, assumes some of the things are constant. For instance, in this case, we're going to let f of t be the constant, let's say f sub 0. So that means, what does that imply? They imply that the surrounding temperature is constant. Which is not that far off from the truth. Pretend that you put something in the refrigerator, the temperature inside the refrigerator is more or less constant. If you leave it outside, even for a long time, the surrounding temperature tend to remain constant for a long time throughout the day. So that's not too far-fetched. And we can also assume that the function u of 0 is equal to u sub 0. That is basically meaning this is our initial temperature of the object. And if I assume these two things, then what will happen to my equation? Well, that will equal to this. So notice that now f of 0 is no longer a function and now can be moved out of the integral, and integral of e to kt dt would just equal to this. And so if you look at this, notice what happened. These all just cancel out, and therefore leave you with this equation. And now if I plug in my initial condition, then that would tell me that u sub 0 equal to f of 0 plus c times e to the 0, which is c, and therefore tell me that c must equal to u sub 0 minus f sub 0. And now it become a much more familiar Newton law of cooling formulas. Okay, I know some of you probably are still thinking like, wait, that doesn't look like the formula I know. Well, it's a matter of notation being used differently. So I'm going to go and write it into probably what I think, like in physics, the formula you probably learn. So remember, F sub 0 is the surrounding temperature and U sub 0 is the initial temperature. So I think that's probably the formula that you probably remember from either physics or in algebra 2. All right, unfortunately that's all the time we got. And that's all the things I want to show you in 2.1. Yes, I know yesterday I was thinking I was going to squeeze into one video, but then since I'm doing a second video, I might as well talk a little bit more about and give you a few more examples. That's the reason why today's video is also kind of long, but it's less than 30 minutes, so I guess it's okay. All right, I'll talk to you guys next time, okay? Bye-bye.